Let me make use of this opportunity to welcome you to computer assisted application class. Today we are going to continue our discussions on fuzzy logic controller. Before I will go to today's discussions, let me take the class through our memory lane. Before today, I have um, I have uh, I have taken the class through building and development of a fuzzy inference system using fuzzy logic app in MATLAB environment. That particular method is okay and is fantastic. Notwithstanding, we still have another option of developing fuzzy inference system. Instead of making use of app, we can write our program. We can write MATLAB program to do the same. And that is what we are going to do today. We are going to develop MATLAB program that we can use to design fuzzy inference system. And to do that, I will take the class through our procedure that we are going to follow if we want to make use of MATLAB script for designing of our fuzzy inference system. After I might have done that, I will now introduce our problem to the class. We will analyze the problem. And after analysis, we are now going to use the procedure that I'm going to introduce you to come up with a MATLAB script. After that second stage, then I will take you to the third stage. The third stage is we are going to realize the MATLAB script that I'm going to take you through in this presentation. We are going to realize it in MATLAB environment. We are going to run it and we are going to evaluate the output so as to be able to know that the procedure that I'm going to introduce you to, is a very fine procedure. So let me now take you to that particular area without wasting time. Yes, as I've told you, we are creating fuzzy inference system by making use of a MATLAB script. We are going to develop MATLAB script by ourselves, and for us to be able to do it very well, I'm going to take you through the procedure that you are going to follow so as to be able to get it right. And that is what we are going to do first. That is, phase one is about development of steps that we are going to use to design or to write or to develop MATLAB program that we are going to use to realize Fusi inference system. This is the procedure, and this particular procedure has 5 steps. Step 1, there is need to give our Fusi inference system a name and to identify whether we are making use of Mamdani or Sugeno. Here we are going to make use of Mandani, and you are going to tell Fusi inference system that you are making use of Mamdani and not Sugeno, and you are going to tell the Fusi inference system the name you are interested in giving to the Fusi inference system you are designing by making use of a command FIX, which stands for Fusi inference system, and tries to identify that you are making use of Mandani. Then try to specify the name you are giving to the Fusi inference system you are going to come up with. Then, after you might have done that, we are now going to step 2. Step 2, you are going to define input and output variables. And when you are doing that, you've known that when we were using Fusi logic hub, you are going to use the command hard input for the input variable. And please don't forget, see how the command is written hard, ADD in lowercase, and the input is going to begin with the uppercase R. And this command is for the input variable, and the number of input variables that you have will dictate the number of hard input that you are going to use. Then for you to be able to define output variables, you are going to make use of the word, the command hard output, and the output is going to start with a capital letter ho. Please don't forget. Then after you might have done this, you know, in Fusi logic controller, there is need for us to set our membership function. That is, the membership function is going to map the Fusi value to the Crisp value. And to do that, as I've told you in our previous lectures, you can make use of trapezoidal membership function. That is, the membership function that makes use of trapezium or trapezoidal shape. You can still make use of triangular shape, and that part of that type of membership function that makes use of triangular shape is referred to as triangular membership function. And the command for the trapezoidal membership function is trap mf, and the one for the triangular membership function is try membership function. Don't forget. Then after we might have set our membership function based on the range given to us, you are going to be given range. You specify the range. So in setting membership function, then there is need for us again, you know, before you add a rule, you see we are going to be given set of Fusi set, and you know, you need to the set of Fusi set is not going to is going to lead you to the number of trapezium and number of triangular membership function that you are going to use in your program. Then after you might have set the membership function, we are now going to add the rules that the inference engine is going to use to do the needful. And for us to be able to do that, we are going to make use of if then statement. And I've told you in our last class that if you are making use of if-then statement, in between if and then, we are going to have antecedent, and after then we are going to have consequence. Like here, temperature is equal to hot happens to be antecedent, and fine is equal to high is referred to as consequence. And we link the antecedent to to consequence by making use of if then statement. Then after you might have done that, the rule of the game is that we need to evaluate, when temperature and when temperature and fan has certain value, you know we need to be able to convert the Fusi value that we obtain at that point to the appropriate value that is going to make the fan either to be high or to be low in this case. Then for us to be able to model that one in a MATLAB environment, we need to specify certain value that is going to be within the range, or that the temperature is operating, and see what is going to be what is going to be the output. Then by making use of the command evaluate Fusi inference system, FIX, average. That is, these are the steps that you are going to follow to be able, to write a program that you are going to use to develop a given or Fusi inference system of interest. So I'm now taking you to the problem we are about to solve. That is, we are developing MATLAB program using this particular problem. Then let us now see. The problem is this: you are tasked with designing a Fusi you are tasked with designing a Fusi logic controller for an air conditioning system that adjusts cooling power based on room temperature and humidity. We have gotten our variables. That is, room temperature and room humidity happens to be our input variables. And the output is going to be cooling power, the cooling power. And the inference system we are about to design will work with the AC system to be able to give the power of the cooling power in a given environment where this AC system is placed. That is, the goal of this problem is to maintain a comfortable environment where the air conditioning system is placed. And with this problem, it is evident that input variables are temperature and humidity. Therefore, we are having two inputs, and the parameter for temperature are this. Range is going to be from 10 degrees centigrade to 40 degrees centigrade, and the Fusi set is cold. The Fusi set are cold, warm, hot, cold, warm, hot, and these are the languages that we are going to use for this Fusi set. For the humidity, which is measured in percentage, the range of this humidity is from 20% to 90%, as you have seen here. And the Fusi set here is dry, comfortable, or humid. Is either the humidity is dry, is either the humidity is comfortable and humid. That is, these are the Fusi set for the humidity and Fusi set for the temperature. Then, having done that, then the output variable that happens to be one variable here from the problem is cooling power, and the range given to us is from 0 degrees, 0% to 100%. Then the Fusi sets are low, medium, high. You know, the combination of temperature and humidity will dictate whether the cooling power should be low, whether the cooling power should be at medium or should be high. Then for us now to be able to tell the inference engine on what to do, there is need for us to be able to come up with rules. And these are the rules here using if then statement. The rules here are three: number one, number two, number three. That is, if temperature is cold, then we use the logic and the humidity is dry, then automatically the cooling power should be low because temperature is already low. Therefore, we are economizing the usage of our AC. And when you economize the usage of your AC, the tariff that you are going to pay will surely calm down. Then, if temperature is warm and the humidity is comfortable, then this warm situation will require medium power. Then cooling power is medium. But the two must be obeyed. The two must be obeyed for cooling power to be minimum. But the third rule is making use of or. If temperature is hot or humidity is humid, anyone that is satisfied here will make cooling power to be high. If temperature is hot and humidity is dry, then cooling power is still going to be high, because that is what we have stated here. And if temperature is cold and humidity is humid, the cooling power will still be high. We have three rules, and we are now going to follow our procedures to be able, our procedure the procedure has 5 steps. We are now going to use the steps in our procedure to come up with a MATLAB script that we are going to run in MATLAB environment, so as to be able to establish that we can build FIX using MATLAB script. Here, we are now having this. We are now having our MATLAB. This is our program. Then the first step, whereby we are now creating a new Fusi inference, and we are giving the Fusi inference system a name temperature, and we are making use of Mandani Fusi inference system. That is, and everything that we do here, we are sending it to the location called FIX. But this particular command is trying to tell us that we are making use of Mandani, and the name of the Fusi inference system we are trying to come up with is temperature control. Then this one should be there like that. Then if you want to change the name from temperature control, you can change that. You are at liberty to do anything here, but this is the standard. Bracket open, you close the bracket and you put the name here. And this is step 1. This one we have now been able to convert our step 1 to what we call MATLAB statement by making use of the command Mandani Fusi inference system. This is it. You open the bracket, you close the bracket, and you put what you want to put here. Now, the name must be here, and put anything you feel like here. Then the next thing now is to add our input. And thereafter we add our output. Then for you to be able to tell FIX, that is Fusi inference system, that you are adding the first input, you are going to use the command add input. And This is where you are adding it, and this is the range of the temperature which happens to be the first input. The range given to us happens to be 1040. From 10 to 40. Then for the second input, which happens to be humidity, then you are going to use the same command, add input FIS, comma, then use rectangular bracket. You start from 20% to 90%. Don't put percent, please. You try to close it, and you declare the name. Then we have only one output variable, and the command there is add output variable. And this time around, the range is from 0 to 100, and the name given to the output variable happens to be cooling power. And we have now been able to settle step 2. This is step 1. This is step 2. We are now going to step 3. Step 3, we are defining our membership function. And we have two inputs, temperature and humidity. And temperature has 3 Fusi set: cold, warm, hot. Therefore, we are going to define membership function for the cold, membership function for the warm, membership function for the hot. And this is what we are doing. FIX, what are we now trying to work with? Temperature. And this time around, we are making use of trapezoidal membership function. But here, this is where it may be a little bit difficult for you, but it's not difficult, because when we were doing physiology control, when we were using physiology control app, we just specify the range. The app tries to create this thing for us, but here you are going to be the one to create that. For instance, we are starting, the range start from 10 to 40. Now, for you now to be able to do it very well, we are now going to look at a situation that, when Fusi value happens to be 0, what happened? Because here we have been told that when Fusi value is 0, at 0 level, nothing happened. But this time around, because when you draw trapezoidal shape, you are going to have something of this nature. See my cursor. That is, we are going to have a rising slope, then you are going to have a constant and the falling slope. For the rising slope here, under normal situation, we are not starting from 0, then we are starting from 10. So 10, we are going to assume that at 10, then Fusi value, when Chris value is 10, the Fusi value is 1. And we are going to maintain that until we get to the end of until Fusi value now tries to decrease. Fusi value is 1 up to when we get to 15. At 15, Fusi value will now be decreasing until it now gets to 0. When Fusi value is now 0, the Chris value that represents the coldness is now going to be 20. And for us to be able to draw trapezium, or trapezoidal shape to represent warm, then don't forget what I told you. The trapezium here must overlap with this. To overlap with the first trapezium, you see, so that when temperature is cold and temperature is warm, we can try to get the Fusi value at that point in time and get a corresponding Chris value. Then, the trapezium here must overlap with the first trapezium. To do that, here we have chosen that the trapezium here we start from when Fusi value is 0, the trapezium is going to the Chris value is going to be 15, which is starting from this area. That is, there is now overlapping. Then by the time the thing is rising at 25, When increase value happens to be 25%, when increase value happens to be 25 degrees centigrade, the Fusi value is going to be 1. And we are going to maintain 1 until we get to 30 degrees centigrade. At 30, then in order to achieve the shape of a trapezium, under normal circumstances, there's going to be falling slope. And slope is going to be falling right from when Fusi value is 1 until Fusi value is now 0. And when Fusi value is now 0, the increased value is now going to be 35 degrees centigrade. And for us to be able to draw the trapezium to represent hotness, under normal circumstances, the trapezium here must overlap with the second trapezium. Then what is now going to happen now is that for us to be able to achieve that aim, in this discussion, we start when Fusi value is 0. Then the increased value is going to be 30. Then it's going to rise, and when that gets to the peak, that is when Fusi value is 1, then the increased value is going to be 35. Then it's going to remain at 1, until the thing gets to 40. And 40 happens to be the last increased value. Then therefore, the trapezium is going to go like that without descending, and that is the end of that. The same thing that we did, the same thing that I've explained for this temperature is going to be the same thing that we are going to do for the humidity. That is, humidity starts from 20 to 90%, and we are having 3 different Fusi sets. And for us to be able to represent this Fusi set very well, we have chosen trapezium membership function. And under normal situation, when Fusi is 0 and Fusi is 1, then the humidity is going to be 20%, and 20% is going to be remain until we get to the point where the falling slope, the slope is going to start falling. It's going to fall from 1 to 0. It's going to fall from 1 to 0, and the falling is going to start from when increased value happens to be 40%, and by the time the Fusi value is 0, the increased value is going to be 60. That is what you have here. For us to be able to realize trapezium shape for the comfortability, then what is going to happen now is that this particular trapezium must overlap with part of the first trapezium here. And that's why we try to say that, when Fusi value, for this particular trapezium is 0, then increased value must be 40. And the thing will start rising until Fusi value is 1. And at that point in time, the increased value is going to be 50. And it's going to remain, Fusi value is going to remain at 1 until it gets to 70. When it now gets to 70%, then we are going to have trailing or falling slope. That is, falling slope is going to start at Fusi value is equal to 1, and the increased value happens to be 70%. But by the time Fusi value is now 0, the increased value is going to be 80, and that is the completion of trapezium, denoting or representing comfortable. Then the trapezium represents humid. Then we have stated that there is need for the part of this to overlap with this, so that when the humidity is comfortable, humid, we can be able to capture the thing very well. So under normal situation, we now start from 70 here. That is, when Fusi value is 0 for the humid, then at Fusi is equal to 0, Fusi value is 0. Then the starting point of the trapezium is going to be 70%, and 70% is now going to be rising. The slope, rising slope, is going to continue like that until Fusi value is 1. And at that point in time, when Fusi value is 1, that one is going to be mapped to the 80%. Then Fusi value is going to be 1 for 81, 82, 83, 84, 85, until you now get to 90. By the time you get to 90, for the triferion to be able to obey its value, it's supposed to go to 0, but 90 happens to be the end. Therefore, we are going to have something of this nature. The trapezium here will not have falling slope. So having done that, we can now go and add membership function for the output. And for the sake of explaining triangular membership function, then we are making use of triangular membership function here. And you know, for the triangular membership function, it has only rising slope and a falling slope. Rising slope and falling, there's nothing like a constant, that is, there's nothing like a straight line there. So therefore, for that one, we are, and the range is from 0 to 100. Here, we have now been able to say that low should be from 0 to 40. Medium supposed to be from 30 to 70, and what have us. Then, what this one is trying to tell us, as I've told you, the rising slope is going to start, when physics value is 0 pu per unit, then the cooling power is going to be 0%. Then, as a physics value is increasing, we are going to have a rising slope. Then by the time the physics value is now 1, then meaning that we are, the cooling power, the increased value of the cooling power is going to be 20%. Then immediately the thing gets to 1, which is a peak, is going to, we are going to experience decreasing slope. And the decreasing slope, by the time physics value now is 0, the increased value for the low is going to be 40, and so on and so forth. And that is how we realize this. Then, having done that, we can now talk about the rules. These are the rules. And you are going to start this discussion. We are going to write the statement here by starting with rectangular bracket, and you close with a rectangular bracket, and you terminate the statement here with a semicolon. And what am I talking here? And since the statement here is terminated with semicolon, meaning that this thing that we are having here, the statement that we are having here, they represent what we call columnar vector, because we have 3 rows and 1 column. And this one represents row number 1, row 1, which is row number 1. This one represents row number 2, and this one represents row number 3. Well, after you might have now declared this rule and you load them into rules variable, or into this location, into this variable location, then you are going to add this rule to fuzzy inference system by making the command add rule. You open a bracket, coil bracket, and you close with a coil bracket, and you terminate with a semicolon. Then fuzzy inference system, and the rules that you have written here, you write it here. And what makes a fuzzy inference system to recognize that it's now adding rule happens to be this command. And don't forget lowercase add. Then beginning of rule is going to be uppercase. Don't use lowercase for R, because MATLAB is sensitive to the case of your command. MATLAB compiler, doesn't, it will differentiate between uppercase R and lowercase r. If you use lowercase r here, you are going to have error. Now, having done that, we have supplied the rule. Then the next thing to do is just to evaluate, what we have done. And at the same time, you may like to see your membership function so that you can try as much as possible to adjust the membership function so that if you don't get expected result. That is what I'm trying to say is that let us believe that instead of terminating, instead of fuzzy value to start decreasing from this area, when you now try, you need to see it so that you can change this value to another thing entirely so as to be able to get another value. So what I'm trying to say is that there is thing for us to plot our membership function, used in a given figure, in a given window. And here I have decided, since I'm interested in having three membership function, which consists two input membership function and one output membership function. I've decided to make use of subplot, and I want them to be in the same on the same figure, and therefore I've been able to use subplot. The work of subplot is that I think I've told you when we were trying to write a program one time like that, but if I've not, the subplot is going to divide a window into what we call row and column. This is how many rows do I want? Here I want 3 rows, 1 row for one membership function. So I have 3 membership function, therefore I have chosen 3 rows. That's why you have 3 here. And since I having 3 plot, I'm interested in just only one column. That is, this is a columnar vector. That is, but I'm not having top top portion for the then we have middle portion and bottom portion. For the top portion, I want input the temperature membership function to be there, and that is 1, and second input to be there, that is 2. Then the third plot, then I want output membership function to occupy that, and that is I'm creating 3 rows, 1 column. Let us believe that I have 6 plot I'm interested in having 6 plot. Therefore, I can have what I call 3 rows, 2 columns, and 2 is going to be here. 3 times 2 is going to give you 6. Then, but you are going to have 3 rows, 2 columns, and you can still do this. But then you are not going to have up to 6 plot. But you may say that no, I want 2 rows, 3 columns, so that it depends on what you want, so as to be able to present your figure in a decent way. Then if that the case, you can have 2 rows, 3 columns, and that one is going to give you two rows, 3 columns. And in that area, we are going to have 2 rows, 3 columns, 2 rows, 3 columns, 2 rows, 3 columns. If you are having 6 plots or what have you, that is the essence of using subplot. So this one is going to show you your membership function, and after you might have gotten that, then for you now to be able to see whether the thing is working very fine, we have chosen 10 degrees centigrade and 90%. Then using this particular this statement and the command of important here, which we have done when we were doing when I was demonstrating the usage of Fuzzy Logic Controller app. I told you that we try to send what we have created to the workspace, and we found it in workspace. We try to move it to the workspace, and at workspace, in order to see what is happening at command window, I told you that you can put output is equal to evaluate, because without this, that is workplace happens to be where after you might have built this fuzzy inference system, and you program it on a given hardware, then that particular hardware is going to be connected to a workable system, so that it's not going to be controlling it. The workable system is referred to as a plant, that I've told you the other time when I was introducing you to the classical control system and fuzzy logic control system. Then I told you that the place that a classical control system is going to occupy is going to be the place where fuzzy logic control system is going to occupy. Then they are not going to be controlling, the plant. Like what we are talking here now, our plant happens to be our AC system. It happens to be our AC system. Then what we are now trying to say is that after you might have finished with this, there is need for you to build it, and after building it, you load it into an hardware, and you now carry the hardware you connect the hardware to the plant so that it's not going to be controlling the plant. Now what I'm trying to say is that, but before you do that, there is need for you to know the performance of what you are going to build on an hardware. Then that is why we move, we move the app, to workspace. And from workspace, we now use ever fix, by you declare fix, and the variable, you now try to pick certain value. This one is for temperature, this one is for humidity. Then you do this, and we run the experiment. After we now run the experiment, this is what we obtain. That is, if temperature is 10 degrees centigrade and humidity is 90%, automatically the cooling power is going to be 80%. It's going to cool, it's going to be this, it's going to be 80%. The room is going to be 80% cooled. And that is and what tries to make this one happens to be this command DISP. I told you in the class that DISP means display. And what we want to display, we wanted to display the content of output. And the content of the output happens to be what this particular statement tries to put here. And you can, any name you give to this area is what is going to be put here. But what is actually important here is ever, fix, and ever, and fix here, and the usage of this bracket. You use this, and you use this, and you use this kind of a bracket here, and you now run your program, and this is what you are going to get. And that is the end of our end of our discussion. Here I have been able to carry the class through the procedure to be followed in order to be able to write good program that we can use for the designing of fuzzy inference system. And for us to be able to demonstrate how to make use of steps under the procedure that we have discussed, I now try to present to the class a problem that has one output, two inputs, and we use Mandani for that. And I try to discuss with the class how we can convert those steps under the procedure to a MATLAB script. And each of the step in our procedure, I discuss it very well. And thereafter, I try to identify important commands that are supposed to be used. And we need to look at them very well. Where you have lowercase, use lowercase. Where you need uppercase, use uppercase. And if you need anything whatsoever, by the time you get to MATLAB environment, you can go for help. Help is going to tell you better. That is what we are trying to say. Now, having finished this, I'm now taking the class to MATLAB environment, where we are going to demonstrate, where we are going to run the program that we have developed here together. I'm now taking you there now. Let us go there. Off we go. Thank you. So by the time we now run, when we get to the MATLAB environment, this is what we are going to see. This membership function for the input 1, which happens to be for temperature. This is membership function for the humidity, and this membership function for the cooling power. You can see that this is a trapezoidal shape. This is trapezoidal shape. That is, this is a trapezoidal shape 3. The first one is representing a cold temperature. The middle one is representing warm temperature, and the third one is representing the third fuzzy set is representing hot. And you can see, this area, this middle membership function overlaps at this particular area, and this particular area is telling us that temperature is there, humidity is there, and here I mean, cold temperature is there. Is either the thing is cold or warm, and here is either the temperature is warm or hot, and anything falls into that particular area, then the decision is going to be made. And the same thing here, this is where we make use of our humidity. And what I'm trying to say is that if you are not interested in the way this one look like, you can extend your this thing to this particular area, so that the thing is going to go like this. So that is that. And if the thing is not giving you expected result, you can just try to come to this area and adjust. And that is why, where we stated 10, 10, 20, 30, or what have you, you can do it in such a way that the thing is going to, before you build, before you program your hardware. And this is a triangle for you. And when we now run the thing, we got when temperature happens to be 10 degree centigrade, and humidity happens to be 90%, we got this. Then having done that, I'm now taking the class to the MATLAB environment, where we are going to simulate or run the program that we have been able to build together. Off we go. Thank you.